Head of the Department and Conference Co-Chair ICACTEA 2026, Dr. T. Sudharani Madam, and Dr. P. Subbarao Sir, Publication Chair ICACTEA 2026, and valued participants and faculty members. My name is Lokesh Reddy from 3rd year CSC. I am delighted to welcome you all to the second day of 3rd International Conference on Algorithms and Computational Theory for Engineering Applications. Day 1 highlighted how artificial intelligence is transforming healthcare and bioinformatics. We understand how AI helps analyze large biomedical data more effectively. It supports early detection and improves diagnostic accuracy. AI also assists doctors in making better clinical decisions. Overall, AI is improving patients' healthcare and accelerating medical research. Now, let's move on to day 2. We have with us another eminent speaker, Dr. Umar Muhammad Sir, President of the Operations Research Institute for Decision Sciences and Analytics, Nigeria. It is my honor to warmly welcome Dr. Umar Muhammad Sir to the second day of 3rd International Conference. Now I request Mr. P. Abhinay from second year CSC to present the profile of Dr. Umar Muhammad Sir.
Distinguished guests, faculty members, and participants, it's a distinct honor to introduce our guest, Dr. Umar Muhammad Sir. He is a senior lecturer in the Department of Operations Research at Modibo Adama University, Nigeria. He has earned his PhD in Operations Research from the prestigious Aligarh Muslim University in India, where he specialized in applied mathematical programming and computing. He has accumulated over 11 years of experience in higher education and research, establishing himself as a leading authority in his field. His impact is further evidenced by his extensive research, specifically in artificial intelligence and multi-objective optimization. He has published more than 60 research articles in international journals and over 1,000 citations. In addition to his articles, he has contributed to the academic literature as an editor of 2 major books on AI and optimization published by Taylor and Francis Press. He holds significant leadership roles, serving as the President and Fellow of the Operations Research Institute for Decision Sciences and Analytics of Nigeria. He serves as Editor-in-Chief of the Nigerian Journals of Operations Research and contributes as a guest editor for high-impact journals like Sustainability and Decision Analytics. He has been honored with the Young Researcher Award and the Research Excellence Award from the Institute of Scholars, India. Ultimately, through his expertise in mathematical programming and soft computing, he brings a unique perspective on how we can use technology for sustainable development. We are truly honored to have him here today.
Thank you, Abhinay. Now I humbly request Dr. Umar Muhammad Sir to kindly deliver the keynote address.
Thank you. Good morning, all. Am I audible, loud and clear?
Yes, sir, audible, sir.
Okay. Sorry. The title is not as sorry, 1 minute, please. You can see the title is not as
Umar,
hello?
we start the session.
No. Can you see my slide now?
No, you have to share the screen.
Okay. 1 minute. Hello, good morning.
A very good morning.
Distinguished professors, faculty members, staff and students. It is my pleasure to be part and parcel of this third international conference on ICACTEA, algorithms and computational and engineering applications. As rightly said, I'm Dr. Omar Modibo from Department of Operational Research, Faculty of Computing, Modibaro University, here in Nigeria. I'm going to present a title on the convergence of multi-criteria decision-making and machine learning, a new frontier for engineering systems and algorithmic theory. And in operational research and in decision science, in computational sciences, in engineering, we cannot do without solving real-life problems using computational approaches. So with the advent of the emerging technology, what I said, I mean artificial intelligence, that which we have data mining, machine learning, and what have you. It's also good to also have a hybrid, that is a convergence between the MCDM and the machine learning. For the overview, theoretical framework, where we integrate the models and the algorithms, and then the mathematical foundations, with some little example related to inventory and supply chain, and then some advanced convergence like toxins and its complexity, and finally we'll be looking at the challenges and ethical consideration while nurturing into the future and direction of our further research. As an introduction, we are all confronted with this dilemma that engineering systems are becoming increasingly complex, we all know, that are characterized by big data. And this big data hello?
Yeah. Voice is audible.
What is happening?
What happened?
Okay, I think in the YouTube. All right. It was a YouTube that I opened from my system, sorry. So I was saying that engineering systems are becoming very complex, and then as such, because of the volume of data, the velocity, the virality, and what have you, we have several objectives that could be conflicting in nature. For example, if you are dealing with costs, and also you are dealing with sustainability, at the same time you are looking at the reliability of the engineering design, you understand? So these are especially conflicting ideas. So therefore you need to find a way of like optimizing these different objectives, and what we call Pareto optimization, so that you can have at least a very reasonable result that is viable within the context of the design, the engineering system. And because of this gap, we have traditional MCDM. It works excellently at structuring preference, but oftenly it struggles with high dimensional dynamic data and what have you. Because of high dimensionality in data, so the traditional MCDM cannot alone go a long way in solving most of the engineering problems. where you have a multi-criteria, you have an alternative choices of action, and then vis-a-vis you have to rank these criteria based on their performance level or reliability or sustainability or even the cost. So exceptional machine learning is a very good one because it can help you recognize patterns and predict future occurrence of the outbreaks or transparent framework for value-based trade-offs. So this informed the choice of this topic, which is a hybrid paradigm that matches the evaluation power of MCDM with the predictive powers of machine learning. Because what MCDM does, it actually rank if you have more than one criteria, multiple criteria, based on performance, based on reliability, based on sustainability. So MCDM can help you rank these criteria into maybe the most suitable, followed by the next, and like that up to the last criteria. Whereas the machine learning will help you to understand the patterns in and evaluate these patterns so that it helps you to predict future occurrences. Looking at the integration model, machine learning as a preprocessor, you can use unsupervised learning, that is like clustering, to group alternatives or supervised learning to predict criteria values. Because each criteria may have a value, especially when you involve decision makers, value judgments in the process of evaluating those criteria. So MCDM as the evaluator can be applied in different ways, and there are several methods for MCDM, one of which we have TOPSIS, technique for order of preference, by similarity to ideal solution. We also have VICO, PROMETE, to rank option based on predicted outcomes. Simply, we have analytical hierarchy process, AHP, and many CDM also extend to the fuzzy set of them. You have the crisp form of the MCDM as well as you have the fuzzy preferences. So feedback loops also play a very important role in the machine learning, especially when you are using reinforcement learning. This will help you to update the decision based on real-world performance. So theoretically, the framework can integrate these models, MCDM and machine learning, and we expect to have a very perfect and suitable result that can be trusted. Coming on to algorithmic frontiers, neural MCDM architectures is simply incorporating preference function directly into neural network loss function. We are all in mathematical and engineering sciences. We do use the loss function, such as a Taguchi function, when you are dealing with production, for example, even in engineering design, at times we may have some product after the complete design. When we come to production, you may have a specification limit of each product. So at times during production, these products may exceed specification limit, or they may result into, they may fall below the specification limit. So in such case, you'll be having additional costs. For example, if it falls below the specification limit, you may end up having have to rework, possibly, or it becomes a scrap. And this is also a cost to the manufacturer, for example. And if it is the production is over specification limit, then it will also lead you to cost of reworking or cost of scrap, as the case may be. So handling it is very crucial, especially in a production line. And there's also uncertainty. So using fuzzy logic and offset theory, alongside machine learning, it can help to manage the stochastic engineering environment because the system can also write out some spare parts. Some part can expire. Okay, during production, you may have faults, so you can carry out fault tree analysis, and then because of the stochastic nature of the system, environmental systems, the fuzzy logic can play a very important role, which is also can be used as an extension of the traditional MCDM techniques. So the scalability of this algorithm is that machine learning enables MCDM to handle thousands of alternatives in real time, dynamic, such as hello. Am I communicating? Hello?
Yeah, it's
Am I
audible.
audible? Hello?
Participants mute చేసి.
Hello?
Yeah.
Yes, sir. Audible.
Okay.
Thank
Now
you.
looking at the frontiers in mathematical foundation, the machine learning as a predictor, we can have linear and nonlinear regression, just one part of it. Before ranking, you must predict the performance criteria J. So if you are dealing with multiple criteria, and then you want to predict a particular criteria, before you do that, before you do the ranking, you must predict the performance. So this is given by this equation, as you can see, while this Yij is the response variable, and then which is it's a relationship between the input feature, which is Si, of the engineering system, vis-a-vis the parameters that learned by the machine learning model. For example, weights in a neural network can serve as this your teacher, while the last term is the random error, which can also follow a particular distribution. If you have it over a long time, it can follow maybe Poisson or normal distribution, as the case may be. So the predicted value of a specific criteria, for example, time to failure, time between failure, okay, or time to repair of a system that has failed, or a component of a system, an engineering system that has failed. So you can predict the time between failures or time to repair as their average. That is mean time to failure or mean time to repair. So this can serve as your response variable, and you'll be able to predict what specific criteria will fail at what time. This will give you more information, and it's a very sensitive, and especially in the engineering system. So normalization in MCDM normally take place before any ranking can take place, because the criteria may have different units of measurement. Maybe you'll be dealing with cost, that is maybe in rupees or in dollars. Okay, you may be dealing with reliability, maybe in percentage. Maybe you'll be dealing with performance output, possibly in time. Okay, so maybe machine time or what have you. Because of the differences in the unit of the criteria you want to, rank. So you need to normalize this criteria, and they are which is given by this a simple equation Rij, which is a matrix, decision matrix that is being normalized, which is a fraction of the individual response variable all over the summation of the entire response variables all squared under the square root. So this is a very easy and straightforward normalization method for an MCDM like TOPSIS or like fuzzy TOPSIS, as the case may be. Now, for an application example, so after this normalization, and then you'll be able to, having the weights of each criteria, you'll be able to use a ranking system. And that will take us to top 6 where you need to use the positive ideal and the negative ideal solutions, as the case may be. So as a scenario-based example, selecting a supplier, for example, if you are dealing as inventory or supply chain problem, if you want to select a supplier based on predicted lead time, in engineering system, hello, hello, am I audible? Okay. Selecting a supplier based on predicted lead time, for example, and sustainability score. So this will give you a weighted aggregation formula, which is a total score SI for supplier I is calculated as this. And this indicates that you are giving them possibly a very proportionate weight, that in which the summation of entire weight will going to give you 1. Now, in such example, the calculation criteria will be lead time, that is criteria 1, predicted by LSTM, for example, in which the first weight is given provinces, and possibly the second criteria being sustainability, that is the expert input, which is rated with 0.4, which is 40% rated. So in this case, supplier A is ranked higher despite lower sustainability. You can see the sustainability is 0.04, which is 40%. It's sustainable, whereas the lead time is ranked 60%. So as such, supplier A is ranked higher despite lower sustainability because the machine learning is significantly better. You cannot compare 60% with 40% in terms of choice. But definitely, the lead time is the time between placing an order and receiving the order is 60%, which is also better than the expert input, which is sustainability, which is 40%. So in that case, machine learning will help support this decision. And then when we talk of the advanced MCDM, the convergence criteria, we have what we call TOPSIS. Simply stands for techniques for order of preference by similarity to ideal solution. It's ideal for engineering because of measures how far a design is from the perfect model. You have an ideal situation, a perfect model, and then you have a design that is at hand. So this technique will help you to measure how far a particular engineering design is from the perfect model. And this will help you to do two different things. First of all, you have to determine the ideal solution, which is the positive ideal and the best predicted values from the machine learning model, because you are talking of hybrid model now. And then you have to also identify the worst predicted values. And vis-a-vis these two values will help you to measure the distance, that Euclidean distance, the distance of alternative I from the ideal solution. And this is given by these two relationships. You can see where this is a positive ideal solution. Positive in the sense that what are the best out of all the criteria and what are the worst. The worst goes for the negative ideal solution. And by there, you'll be able to measure the distance. And after all, you calculate the coefficient, closeness coefficient, which is also given by this. And then the alternative with highest closeness to coefficient to ideal solution, which is closest to 1, is the optimal engineering choice. At times, you may be having, some will be giving you 0.89, 0.99, 0.79. So the one that is very close to 1 is giving you the best option, which is a suggestion for the optimal engineering choice. And vis-a-vis, so this is a simple way of calculating the TOPSIS, which is one of the advanced technique for the MCDM in terms of converging with machine learning for engineering system. And because of, if you want to take care of the uncertainties, then you can move a little bit one step to introduce the fuzzy topses, which is where you encounter the linguistic terms that are stochastic in nature. So you'll be able to take care of this fuzziness in the system. So algorithmically, in the context of algorithmic theory, the convergence affects computational complexity. For example, machine learning training, where you have a sample size, features, and the iterations it undergoes before it understands the behavior of that system. And then in MCDM, you need to rank these alternatives. You may have M alternative and N criteria. So each criteria can equally and possibly be under a particular alternative. So having these weights, you'll be able to rank which alternative is the best and then which criteria is the most needed for that particular scenario. And in terms of the convergence, the impact is a hybrid approach which allows pruning where machine learning filters the search space. When you have a feasible space within which you have your feasible solution, and you know all the solutions are feasible, but they cannot be optimal. You definitely have to search for the optimal or near optimal solution for you to have a very reliable system in your design and even applications. So reducing M before the computationally expensive MCDM weights are applied. So you apply different weights to help you reduce this kind of weight. And then finally, we have challenges and ethical consideration, and especially you are using these emerging technologies, machine learning, artificial intelligence. Like explainable artificial intelligence, the challenges is in terms of a black box. Machine learning model provide justification that align with mathematical prediction, that is the MCDM logic, that is multi-criteria decision making. Whereas if you come to the data quality, you know, as garbage in, garbage out, whatever you input, that is what you expect to get out. So there's a risk in also automated decision system. So if you are not careful, whatever you assign, you write a code, for example, a program, it will just run out what you expected to do. So it's just like garbage in, garbage out. So there's also a risk in most of the automated systems. But then, if a careful is not taken, then it can run into catastrophe. Therefore, it's a very challenging and ethical consideration has to be considered when inputting the data. You have a quality data, is your data genuine? Because some of this application has to do with real life, have to do with human beings, you understand? So you have to be extra careful in terms of the quality of data you are using. Also, some algorithms have biasness. So you have to ensure that weights in MCDM do not inadvertently amplify biases present in training data, because you have to go beyond training data, maybe 30, 70, understand, you have to go beyond that and see the behavior of the system. So algorithm, and in terms, if you give a very less criteria, a higher weight, that will lead to biasness in the algorithm. And on future directions, you know, the rise of autonomous decision agents. Now we have Industry 5.0, from Industry 4.0 to 5.0, and then you have autonomous vehicles. You can see what is happening now. The system man aircraft and what have you, systems that learn and decide without human intervention. And that is the area we are now in artificial intelligence. You can design a system that can go and execute a task without even a human intervention. So this is also a future area, and that is area that is booming in most advanced countries. And you know, also if you talk of quantum computing, as a potential area for solving NP-hard optimization problem in a hybrid model of MCTM and machine learning space. And then the conversion is not just a trend, it's a necessity for the next generation of intelligent engineering because this is from using probably a traditional or one way of doing it. We have to have an assembled approach. Different methodologies come together to give us a more robust, technique to address our engineering problems. And then in conclusion, we say the integration of the machine learning's predictive power with multi-criteria decision-making evaluate framework marks a paradigm shift in engineering, enabling systems that are both data-driven and strategically aligned. This convergence transforms raw complexity into actionable intelligence, paving the way for next-generation algorithm theory and sustainable industrial applications. So as a take-home, you have to bridge the gap between predictive modeling and value-based judgment to build more resilient, transparent, and optimized engineering solutions for the future to generations. So I think I will stop here, and I want to appreciate everyone. If there are questions or answers, I will be happy to take them or comment from any of the participants or faculty members or students so that we can share ideas on this platform. And if there is something, I wish to thank each and every one of us. Thank you very much.
Thank you, sir, for your thought-provoking keynote address. Your words have truly enriched this conference. The keynote highlighted the integration of multi-criteria, decision-making, and machine learning. It showed how combining these approaches helps solve complex engineering problems more effectively. This convergence opens new possibilities for smarter engineering systems and advanced algorithmic research.
I can't hear you. You are muted. Please unmute yourself. Hello, I can't hear you, please.
Sir, is it audible? Sir, am I audible?
Yes, now you are audible.
Okay. Thank you, sir, for your thought-provoking keynote address. Your words have truly enriched this conference. This keynote highlighted the integration of multi-criteria, decision-making, and machine learning. It showed how combining these approaches helps solve complex engineering problems more effectively and efficiently. This convergence opens new possibilities for smarter engineering systems and advanced algorithmic research. I request everyone to actively participate in the presentations and share your valuable perspectives. Thank you for your continued dedication and enthusiasm throughout the session. Let us make this day as productive and inspiring as the previous one. Participants are requested to kindly join in the online tracks for the presentations. Thank you one and all. And now we will have some tea break. Snacks are available outside.
Thank you, sir. I'm Dr. T. Sudharani, head of the department. I'm very much thankful to you for your. We are invited you for the short notice, but you attended and gave an insightful session. Thank you so much for your participation and your talk. Thank you so much, sir.
You're welcome, Ma. Thank you very
sir.
much.
Thank you, sir. We look forward to you for our upcoming events also. Thank you, sir. Very nice of you.
Thank you. You are very much welcome. And also, I want to thank my friend, Dr. Professor Subram,
Yes, sir.
who we have been together.
Yes,
for
sir.
over
Definitely, we
5
should
years.
appreciate the efforts of Dr. P. Subbarao, sir. Through him only we will actually got your time. Thank you, sir. Thank you so much for joining.
You are most welcome. You are most welcome.
Bye, sir. Good
It's
day.
my pleasure.
Bye, sir.
Good day. Have a wonderful conference. I wish you a successful deliberations. Thank you.
Yes, sir. Yes, sir. Thank you. Thank you so much.
Thank you.